Trades. In year 1817, John Wolfgang Daubernier, a German chemist tried to arrange the elements with similar properties into groups. He identified some groups having three elements each, so he called these groups triads. Daubernier showed that when the three elements in a triad were written in order of increasing atomic masses, the atomic mass of middle element was roughly the average of the atomic mass of the other two elements. For example, take triad consisting of lithium Li, sodium Na, and potassium K, with the respective atomic masses 6.9 to 23.0, 39.0. What is the average of the atomic masses of Li and K? How does this compare with atomic mass of Na? Given below table 5.1 are some groups of three elements. These elements are arranged in downwards in order of increasing atomic masses. Can you find out which of these groups are from the Aubernier traits? You will find that group E and C from Daubernier traits. Daubernier could identify only three traits from the elements known at that time. Figure table 5.3. Hence, this system of classification into triads was not found to be useful. John Wolfgang Daubernier studied as pharmacist at Munich in Germany, and then studied chemistry at Strasbourg. Eventually, he became a professor of chemistry and pharmacy at University of Jena. Daubernier made the first observation on platinum as a catalyst and discovered similar traits of elements which led to the development of periodic table of elements. Newland's law of octaves. The attempts of Daubernier encouraged other chemists to correlate the properties of elements with their atomic masses. In 1866, John Newland, can an English scientist, arranged the known element in the order of increasing atomic masses. He started with the element having the lowest atomic mass, hydrogen, and ended at thorium, which was the 56th element. He found that every eighth element had properties similar to that of first. He compared this to the octaves found in music. Therefore, he called it law of octaves. It is known as Newland's law of octaves. In Newland's octaves, the properties of lithium and sodium were found to be the same. Sodium is the eighth element after lithium. Similarly, beryllium and magnesium resemble each other. A part of the original from Newland's octaves is given in table 5.3. Are you familiar with musical notes? In Indian system of music, there are seven musical notes in a scale: sa re ga ma pa da ni. In West, they use the notations do re mi fa sol la ti. The notes in a scale are separated by whole and half step frequency intervals of tones and semitones. A musician uses these notes for composing the music of a song. Naturally, there must be some repetitions of notes. Every eighth note is similar to the first one, and it is the first note of the next scale. It was found that law of octaves was applicable only up to calcium, as after calcium every eighth element did not possess properties similar to that of first. It was assumed by Newlands that only 56 elements existed in nature and no more elements would be discovered in future, but later on several new elements were discovered whose properties did not fit in the law of octaves. In order to fit elements into his table, Newlands adjusted two elements in the same slot, but also put some unlike element under the same note. Can you find examples of these from table 5.3? Note that cobalt and nickel are in the same slot and these are placed in same column as fluorine, chlorine and bromine, which have very same properties than these elements. Iron, which resembles cobalt and nickel in properties, has been placed far away from these elements. Thus, Newland's law of octaves worked well with lighter elements only. Making order out of chaos, Mendeleev's periodic table. Even after the rejection of Newland's law of octaves, many scientists continue to search for patterns that correlated the properties of elements with their atomic masses. The main credit of classifying elements goes to Dmitry Ivanovich Mendeleev, a Russian chemist. He was the most important contributor to the earlier development of periodic table of elements, wherein the elements were arranged on the basis of their fundamental property, the atomic masses, and also on similarity of chemical properties. Dmitry Ivanovich Mendeleev was born in Tobolsk in western Siberia, Russia on 8 February 1834. After his early education, Mendeleev could join an university only due to effort of his mother dedicating his investigations to his mother. He wrote, "She instructed with example, corrected with love, and traveled with me to places, spreading her last resources and strength. She knew that with the aid of science, without violence, with love but firmness, all situations, untruth, and errors can be removed. The arrangement of elements has he proposed is called Mendeleev's periodic table. The periodic table proved to be unifying principle in chemistry. It was the motivation of for the discovery of some new elements. When Mendeleev started his work, 63 elements were known. He examined the relationship between the atomic masses of the elements and their physical and chemical properties. Among chemical properties, Mendeleev concentrated on compounds formed by elements with oxygen and hydrogen. He selected hydrogen and oxygen as they were very reactive and formed compounds with most elements. The formulae of hydrides and oxides formed by an element was treated as one of the basic properties of an element for its classification. He then took 63 cards and on each card he wrote down the properties of one element. He sorted out the elements with similar properties and pinned the card together on a wall. Observed that most of the elements got a place in a periodic table and were arranged in the order of increasing atomic masses. It was also observed that there occurred a periodic recurrence of elements with similar physical and chemical properties. In this basis, Mendeleev formulated a periodic law which states the properties of elements are the periodic function of their atomic masses. Mendeleev's periodic table contains vertical columns called groups and horizontal rows called periods. Mendeleev's periodic table was published in German Journal in 1872. In the formula for oxides and hydrides at the top of the columns, the letter R is used to represent any of element in the group. Note the way formulae are written. For example, the hydride of carbon CH4 is written as RH4 and the oxide CO2 as RO2. Of Mendeleev's periodic table. While developing the periodic table, there were a few instances where Mendeleev had to place an element with a slightly greater atomic mass before an element with a slightly lower atomic mass. The sequence was inverted so that elements with similar properties could be joined together. For example, cobalt mass 58.9 appeared before nickel, atomic mass 58.7. Looking at table 5.4, can you find out one more such anomaly? Further, Mendeleev left some gaps in his periodic table. Instead of looking upon these gaps as defects, Mendeleev boldly predicted the existence of some elements that had not been discovered at that time. Mendeleev named them by preferring a Sanskrit numerical Ika1 to the name of preceding element in the same group. For instance, scandium, palladium, and germanium, discovered later, have properties similar to Aka boron, Aka aluminum, Aka silicon, respectively. The properties of Aka aluminum predicted by Mendeleev and those of elements gallium, which was discovered later and replaced Aka aluminum, are listed as following. This provided convincing evidence for both the correctness and usefulness and of Mendeleev's periodic table. Further, it was the extraordinary success of Mendeleev's prediction that led chemists not only to accept his periodic table but also recognize him as originator of the concept in which it is based. Noble gases like helium He, neon Ne, and argon Ar have been mentioned in many contexts before this. These gases were discovered very late because they are very inert and present in extremely low concentrations in our atmosphere. One of the strengths of Mendeleev's periodic table was that when these gases were discovered, they could not placed in a new group without disturbing the existing orders. Limitation of Mendeleev's classification. Electronic configuration of hydrogen resembles that of alkali metal. Like alkali metals, hydrogen combines with halogens or oxygen and sulfur to form carbon to form compounds having similar formulae as shown in example here. One on the other hand, just like halogen, hydrogen also exists as diatomic molecules, and it combines with metal and non-metal to form covalent compounds. Certainly, no fixed position can be given to hydrogen in periodic table. This was the first limitation of Mendeleev's periodic table. He could not assign a correct position to hydrogen in his table. Isotopes were discovered long after Mendeleev has proposed his periodic classification of elements. Let us recall that isotopes of an element have similar chemical properties but different atomic masses. Thus, isotopes of all elements posed a challenge to Mendeleev's periodic law. Another problem was that the atomic mass do not increase in a regular manner in going from one element to next. So it was not possible to predict how many elements could be discovered between two elements, especially when we consider the heavier elements, making order out of the chaos the modern periodic table. In 1913, Henry Moseley showed that the atomic number of an element is more fundamental property than the atomic mass as described below. Originally, Mendeleev's periodic law was modified and atomic number was adopted as the basis of modern periodic table, and the modern periodic law can be stated as follows. Properties of elements are a periodic function of their atomic number. Let us recall the atomic number gives us the number of protons in the nucleus of an atom, and this number increases by one is going from one element to next. Elements when arranged in order of increasing atomic number z led us to classification known as modern periodic table. Prediction of properties of elements could be made with more precision when elements were arranged on the basis of increasing atomic number. As we can see, modern periodic table takes care of three limitations of Mendeleev's periodic table. The anomalous position of hydrogen can be discussed after we see that are the basis on which the position of elements in modern periodic table depends. Position of elements in the modern periodic table. The modern periodic table has 18 vertical columns known as groups and 7 horizontal rows known as periods. Let us see what decides the placing of an element in a certain group and period. You will find that all these elements contain the same number of valence electrons. Similarly, you will find that the element present in any one group have the same number of valence electrons. For example, elements fluoride F and chlorine Cl belong to group 17. How many electrons do fluorine and chloride have in their outermost shell? Hence, we can say that groups in the periodic table signify an identical outer shell electronic configuration. On the other hand, the number of shells increases as we go down the group. There is an anomaly when it comes to the position of hydrogen because it can be placed either in group 1 or group 17 in first period. Can you say why? You will find that these elements do not have the same number of valence electrons and they contain the same number of shells. You also observe that the number of valence shell electrons increase one by unit as the atomic number increases by 1 unit on moving from left to right in a period. Or we can say that atoms of different elements that with the same number of occupied shell are placed in same period. Na, Mg, Al, Si, P, Cl, and Ar belong to the third period of the modern periodic table. Since the electrons in the atoms of these elements are filled with K, L, and M shells, we write the electronic configuration of these elements and confirm the above statement. Each period marks a new electronic shell getting filled. How many elements are there in first, second, third, and fourth period? We can explain the number of elements in these periods based on how electrons are filled in various shells. You will study the details of this in higher classes. Recall that the maximum number of electrons that can be accommodated in a shell depends on formula 2n square, where n is number of the shell per give from the nucleus. For example, K shell 2 into 1 square equals to 2, KL L shell 2 into 2 square equals to 8, M shell 2 into 3 square equals to 18. Hence, the first period has 2 elements, hence, the second period has 8 elements. But the outermost shell can have only 8 electrons, so the third period also have only 8 electrons. The position of an element in the periodic table can tell us about its chemical reactivity. As you have learned, the valence electrons determine the kind and number of bonds formed by an element. Can you say why Mendeleev's choice of formula of compound as the basis for deciding the position of an element in his table was a good one? How would this lead to elements with similar chemical properties being placed in same group? Trends in modern periodic table. As valency, as you know, the valency of an element determined by the number of valence electrons present in the outermost shell of its atom. Atomic size. The term atomic size refers to the radius of an atom. The atomic size of may be visualized as the distance between the center of nucleus and the outermost shell of an isolated atom. The atom radius of hydrogen atom is the atomic radius of hydrogen atom is 37 pm picometer. 1 pm equals to 10 minus 12 m. Let us study the variations of atomic size in a group and in a period. You will see that the atomic radius decreases in moving from left to right along a period. This is due to increase in a nuclear change, which tends to pull the electrons closer to the nucleus and reduce the size of atoms. You will see that the atomic size increases down the group. This is because new shells are being added as we go down the group. This increases the distance between the outermost electrons and the nucleus, so that the atomic size increases in spite of increase in nuclear change. Metallic and non-metallic properties. As we can see, the metals like Na and Mg are towards the left side of periodic table, while the non-metals like sulfur and chlorine are found on right side. In the middle, we have silicon, which is classified as a semi-metal or metalloid because it exhibits some properties of both metals and non-metals. In modern periodic table, a zigzag line separates metals from non-metals. The boundary line elements boron, silicon, germanium, arsenic, antimony, tellurium, and polonium are intermediate in properties and are called metalloids or semi-metals. As you have seen in chapter 3, metals tend to lose electrons while forming bonds, that is, they are electropositive in nature. As the effect nuclear change acting on the valence shell electrons increases across a period, the tendency to lose electrons will decrease. Down the group, the effective nuclear change experienced by valence electrons is decreasing because the outermost electrons are further away from the nucleus. Therefore, these can be lost easily. Hence, metallic character decreases across a period and increases down a group. Non-metals, on the other hand, are electronegative. They tend to form bonds by gaining electrons. Let us learn about the variation of this property. As they tend as the tense in electronegativity show, nonmetals are found on the right hand side of periodic table towards the top. These trends also help us to predict the nature of oxides formed by the elements, because it is known to you that the oxide of metals are basic and that of non-metals are acidic in general.